Yeah. Now get just 2 minutes more. Okay, right. Yeah. Good morning, all of you. Yeah. Yesterday we have. Pardon? Yeah. I guess I'll come into that, right? Okay. Yesterday we have completed calculus, that is uh, limits, continuity, differentiability, different integration, improper integration, and then mean value theorem, and so on and so forth. Yeah, there are some queries, some questions, some mails from some of our friends saying that it's too fast. Are you able to follow? Are you able to listen, all of you? Hello? Okay. Right. Thank you. Okay. So some of the mails I have responded because it is a stipulated time. I have to go a bit fast. Otherwise, we cannot. It is very difficult for me to complete the syllabus. The first thing, second thing, for your convenience today, I am using a mouse so that you can follow it clearly. The third one is someone asked me a question. Explain what is the domain of a function with the example. Yes, this is the answer for that. Please, whoever it is, please follow this. The domain of a function is the set of all possible inputs. That is the set of input values where for which the function is defined. So if you define a function, what are the values it can take as input? They are all called, that the set of all those points is called domain. So for example, when we use the function notation f from R to R, this R is called domain, this R is called codomain. We mean that if a function from the real numbers to the real numbers. In other words, the domain of f is a set of real numbers and it's the set of all possible outputs of our codomain is also the set of real numbers. So for example, if you define the function fx is equal to square root of x minus 1. So what happens here is when x takes less than 1, what happens? Let us say, for example, if I take x is equal to 0, what happens? We get square root of minus 1. What is that? Square root of minus 1 is imaginary quantity. So it is not a real quantity. So here the function from R to R is not satisfying this property. So what should be the condition here? For any x less than 1, we are getting a imaginary quantity. So what should be a possible value for input of this function? X must be greater than or equal to 1. If x is equal to 1, this will be 0. X greater than 1, square root of positive quantity, that is a real number. So here the domain will be x greater than or equal to, x belongs to R and x greater than or equal to R, that is the domain here. So we typically assume the domain is the largest subset of real numbers where f could be defined. In this example, we would implicitly understand the domain is a set of real numbers greater than or equal to 1. Hope the doubt regarding the domain is clear, my friend. So he is one question he has asked me about the domain. So if you have any doubts, you are free to, I welcome you all. If you have doubts, you can ask me. I will try to answer the questions. Okay. Coming to the today's concept. Yesterday we have finished off actually Lagrange's mean value theorem and Taylor's mean value theorem also. But somebody said that Taylor's theorem we have gone a bit fast, sir. It is a bit fast. Explain once again. Taylor's theorem and Lagrange's Maclaurin series expansion. So briefly, just revisit the concept of Taylor's theorem, that is called generalized mean value theorem. You don't worry about the noting down the formula, right? All these PPTs will be given to you, will be present, will upload in the website. You can download and you can see whenever you want. Don't worry about the PPTs. Okay, they are with you. Take it granted. Okay, understand, listen to my words very clearly. If you have any doubt, you can send a mail to me. I will explain you once again. Okay, I will tell you, I give the clarification to you. Now, once again, as somebody asked me what is the Taylor's theorem, explain once again. Suppose function f satisfies the following two conditions: fx and its n-1 derivatives. N-1 derivatives means first derivative, second derivative, third derivative till n-1 derivatives are continuous in closed interval AB, and fn-1 is differentiable. That means n- first derivative is also differentiable. So n-1 derivatives are continuous and n-1 derivative is also differentiable in open AB. Then there exists at least one point C in open interval AB such that f of b is equal to f of a plus b minus a f dash a plus b minus a whole square by 2 factorial f double dash a, so on and so forth. This is called Taylor's theorem. So an offshoot of this Maclaurin's theorem, a substantial result of Maclaurin's theorem is if you put b is equal to x and a is equal to 0 in this, b is equal to x means this becomes f of x and a is equal to 0. This is f of 0 plus x minus 0, f dash 0, x minus a whole square by 2 factorial, so on and so forth. That is given by Maclaurin's theorem. Maclaurin's theorem is also known as Taylor's theorem, Taylor's expansion about x is equal to 0, because here the functional values are defined at f. So these are called Taylor's theorem about x is 0, that is called as Maclaurin's expansion of a function. So this is very much useful for us, and in earlier gate papers also there are some questions on the expansions of Maclaurin's expansions or function expansions. They have asked what is the expansion of e power x sin x, something like that, earlier gate papers. So when such problem is asked, very clear, very quickly you can write the function using Maclaurin's expansion. What all you have to do is find the function value f of 0, derivative at 0, f double derivative at 0, so on and so forth. We get the expansion of any function that is asked. Okay. The next thing is, see, for example, prove that tan inverse x is equal to, find the expansion of tan x. Maybe it may not be in the gate examination, it may not be a question like this, prove that, show that, do something. What is the expansion of tan inverse x, and it will be given 4 alternatives A, B, C, D. So in such case, this is expansion about pi by 4. See, here expansion about 0 means we are getting f of 0, f dash 0. Here I am writing as pi by 4. So that means expansion about pi by 4 are in the increasing powers of x minus pi by 4. If you go back here once, Taylor's theorem, if you put b is equal to x and keep a as it is, what happens? F of x is equal to f of a plus x minus a, f dash a plus x minus a whole square by 2 factorial, f double dash a, so on and so forth. This we use here for this problem. So if we put a is equal to pi by 4 and b is equal to x, the Taylor's theorem, this is what we get. So only thing you have to do is you have to find f dash, f double dash, so on and so forth. So for f of x is equal to tan inverse x, f of pi by 4 is tan inverse pi by 4, f dash x is 1 by 1 plus x square. We know that derivative of tan inverse x is 1 by 1 plus x square. F dash pi by 4 is 1 by 1 plus pi square by 16. F double dash is minus 2x by 1 plus x square whole square. So this is the value of f double dash at pi by 4. So substitute all these things in this expansion. What is that? In this expansion, this one. Okay. So this is finally what we get. Tan inverse x is equal to tan inverse pi by 4 plus x minus pi by 4 by 1 plus pi square by 16, so on and so forth. This is how we get the series expansion of any function. So obtain the Taylor series expansion of f of x is equal to cos x about x is equal to pi by 3. As I told you, when you are asked to find the Taylor series expansion about a point, you have to put b is equal to x and a is equal to whatever point that is asked here. So what is the point here? X is equal to pi by 3. So again, once again go back to the formula. So this is what we have, Taylor's theorem. If you put b is equal to x and a is equal to pi by 3, that's given the f of x is equal to f of pi by 3 plus x minus pi by 3 f dash pi by 3, so on and so forth. This is what we do here. So in the powers of x minus pi by 3, so f of pi by 3. So summation form low, if you write that expansion Taylor's theorem in summation form, this is what we get. So f of pi by 3 is cos pi by 3 is 1 by 2. F nth derivative of cos nx is cos x plus n pi by 2. If you put pi by 3, cos x is so on and so forth. This is the expansion of this thing. And one more thing that is asked in the problem is approximate value of cos 61. Maybe it may not be an essay question in the gate examination, but it may be like this. Find the expansion of cos x. The expansion of cos x about the point pi by 3. A, option B, C and D. Then you have to go this way and this is what you get finally. So expand log x in powers of x minus 1 and hence evaluate log 1.1. So clearly fx is equal to log x, log 1, because the expansion is about 1 here. In the powers of x minus 1 he is asking you. So you have to get the functional values and its derivative at x is equal to 1. So f of 1 is log 1 is 0, f dash x is 1 by x, f dash 1 is 1, f double dash x is minus 1 by x square, f double dash 1 is minus 1. Then again if you differentiate this 2 by x cube or at 1 the value is 2, so on and so forth. So again if you go back to the formula, f of b is equal to f of a plus x minus a into f dash a, so on and so forth, Taylor's theorem. Then you put all these things, we get log x is equal to x minus a, so on and so forth. So, okay, this is how you have to find the problem. Maybe the expansion of log x in powers of x minus 1 is a, b, c, d options. So you have to do this part of this and then you'll get this answer like this. Okay, that is about expansion of e power sin x by Maclaurin series up to the term containing x power 4. Sometimes in the examination you may be asked to find up to what term you have to get the series expansion. The series may first two terms may be a, b, c, d in the options. In the first two options, the first two terms may be same, maybe third and fourth term may change. You have to be very careful. So e power sin x, f of 0 is at 0, sin x is 0, sin 0 is 0, so e power 0 is 1, f dash is f of x into cos x, that means e power sin x into cos x, so that is f dash 0 is 1, f double dash is again 1, you calculate these derivatives at 0, these are the values we get, f fourth derivative is minus 3. And put that in Maclaurin series expansion. What is Maclaurin series expansion? So, just we'll go back to Maclaurin series once, then you'll understand better. F of x is equal to f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash 0, so on and so forth. This is Maclaurin series expansion. Okay, if you put that here, you get f of 0, that is 1, plus x into f dash 0, 1, plus x square by 2 factorial into f double dash 0, 1. Next term is x cube by 3 factorial, f triple dash is 0, you don't have this term. So x power 4 by 4 factorial into minus 3. This is what we get. This is how we solve the problems in Taylor's and Maclaurin series expansion. Some problems are given to you. Somebody asked me the solutions. I will try and provide to give the solutions to you. Okay. The next idea, this is actually minimum, this mean value theorems we have finished off. Another expansion I am giving it to you, that once again, that's all. Now, next idea is local maxima and minima. A function f of x is said to have a maximum value at x is equal to, see, this question, the definition of maxima and minima, sometimes it was asked in a GATE and a JRF also, only a multiple choice question in paper 1. So be very particular about the definition also. It is, don't note that it is a local maxima and minima. The word local is very important here. The function f of x is said to have a maximum value at x is equal to a if there exists a small number h such that f of a is greater than f of a minus h and f of a plus h. That means, what is the meaning of local is, if you take a point x is equal to a, in the neighboring points, local means your neighbors, right? Local to your residence means your neighbors. So, if you take any neighboring points of this x is equal to a, and you have maximum value at a, means f of a must be greater than any other value of the function in the neighborhood. That's what we mean. So such that f of a is greater than f of a minus a. Now we can obviously write the definition of the local minima. What happens? For any it has a local minimum value at x is equal to a if there exists a small number h such that f of a is less than in between a minus h to a plus h, f of a must be the minimum value. A function f of x is said to have a minimum value at x is equal to a if there exists a small number h such that f of a is less than f of a minus h and f of a in the interval a minus, because it should not both these should not be there. In between these, in this interval a minus h to a plus h, here also a minus h to a plus, well, it should be maximum here, it should be minimum here. So the maximum and minimum values of a function taken together are called the extreme values. Extreme values means it can be a maximum value or it can be a minimum value. In general, we use the word extreme value to represent both minimum and maximum. And the points at which the function attains or gains the extreme values are called turning points of the function. That means it goes to the maximum. Say for example, if you understand, like, let us say this is my function, right? Okay, this is a small neighborhood. In this interval, this function has a maximum value here. So this is what we call local maximum. If this is a small interval, so this point is at this point the curve is having the function is having maximum value. Say for example, I have curve like this now. This is the interval. So this will be our local minimum because this is x-axis, y-axis like this. So this will be a minimum value, and in this case it's the maximum value. This is what exactly we mean by minimum and maximum values. Any point at which the concavity of the function changes from up to down. We have discussed this concept actually, concave upwards and concave downwards in yesterday's class. Anyhow, from up to down or vice versa is called point of inflection. We have studied this, we have done problems also on points of inflection, concave downwards, concave upwards and all that. At a point of inflection, either d square y by dx square is equal to 0 or d square y by dx square does not exist. Procedure for finding the maximum and minimum. What is the procedure to find the maximum and minimum? Let the given function be, call this function as f of x. Find f dash x and equate it to 0. That is the first step to find discuss the maximum minimum. Equate to 0. Solve this equation and you will get the roots of x as a, b, c, whatever it is. You will get some roots of x by equating f dash x is equal to 0. The next step is f double dash x, find f double dash x and substitute the points a, b, c in f double dash x. Find f double dash x and substitute the point a, b, c in f double dash x. If f double dash at a point a is negative, then f of x is maximum at x is equal to a. And f double dash is positive, then it is minimum at x is equal to a. This is a simple test. We have to find only first derivative, equate it to 0, you will get the values of x as a, b, c, so on and so forth, whatever it is. Then find f double dash x, substitute these points here. Wherever f dash is positive, you get a minimum. Whenever it is negative, you get a maximum. Sometimes f double dash x may be difficult to find, or f double dash x may be 0 at x is equal to 0. In such cases, f dash x changes signs from negative to positive, or x passes through a. F is minimum at x is equal to a. If f dash x does not change sign when passing through x is equal to a, then f of x is neither maximum nor minimum at x is equal to a. So the procedure is very important. Step 1, 2, 3 and 4. These 4 steps are very important to solve the problems. Let us say some examples. So find the maximum and minimum values of 3x power 4 minus 2x cube minus 6x square plus 6x plus 1 in the interval 0 to 2. So let this be function be fx. Call this as a function f of x. So first thing that we have to step 1 is find f dash x and equate to 0. What is this f dash x is 12x cube minus 6x square minus 12x plus 6. And that I have factorized this. I get 6 into x square minus 1 into 2x minus 1. So then equate this to 0. When we equate this to 0, you will get the roots of x. So that's what I said. See, find f dash x and equate to 0, solve this equation and we'll get the roots of ABC. Okay? So when you equate this to, what are the roots here? X is equal to 1 by 2, one thing. Other one is x is equal to plus or minus 1. These are the roots. Now, find f double dash x. That means when f dash x is equal to 0 at this point, what we mean is f dash x has either minimum or maximum at these points. Then we have to find at which points this function has minimum and maximum. Okay. And one more thing that you have to mind is the given interval 0 to 2. I want to find maximum or minimum values of this function only in the interval 0 to 2. So out of the 3 roots, what are the points which are lying inside this? One is 1, it lies clearly in this interval. 1 by 2 lies in the interval. What about minus 1? It's not there in the interval. So forget about, leave this minus 1. Okay. So in the interval 0 to 2, we can have maximum or minimum at x is equal to 1 by 2 or 1. Okay. Then find f double dash. What is f double dash? This is 12 into 3x square minus x minus 1. Now substitute the points x will 1 by 2 and 1. F double dash 1 by 2 is minus 9. F double dash 1 is equal to 12. Using the procedure, step 3 in the procedure, whenever you have negative value for f double dash, we have f has maximum. So fx has maximum at x is equal to 1 by 2 because f double dash is negative. And f double dash is positive means then we have minimum at x is equal to 1. That's the maximum value of f of 1 by 2. These are the points at which we get maximum and minimum. Then what are the values of the maximum values? Put these points in the function. Then f of 1 by 2 is 2.4375 and the minimum value is f of 1 is equal to 2. Okay. These are the points. X is equal to 1 by 2 and x is equal to 1 are the points and the values are 2.4375 is the maximum and minimum is 1. That means is a local minimum, meaning is if you consider the interval from minus infinity to plus infinity. Plus infinity, when you go to plus infinity, what happens in this function? Goes to infinity. So what is the maximum value? It goes to infinity. When you substitute minus infinity, what you get? You get minus infinity. So for the function over the complete real numbers, the minimum and maximum are minus infinity and plus infinity. We don't want that maximum values over the complete real number. What we want, we are considering a small interval here. Maybe we can call it a small. And in this interval, we are finding the maximum and minimum. That's why this concept is called local means maximum and local minimum, not global one. So that sin x into 1 plus cos x have maximum value at x by 3. Or else, maybe in the examination, the problem may be not like this. The function, where does this function sin x into 1 plus cos x has a maximum value? X is equal to pi by 3, b x is equal to minus pi by 3, c x is equal to 0, d x is equal to pi by 2, maybe e is none of the above. options may be given. What you have to do is, let this function f of x is equal to sin x into 1 plus cos x. First thing first, that is first find the derivative f dash x and equate to 0. So what is the derivative? 1 plus cos x, UV formula, sin x into 1 plus cos x, apply this to is 1 plus cos x into, so this is what we get. Okay. So if you equate f dash x is equal to 0, we get cos x is equal to 1 by 2 or cos x is equal to minus 1. These are the two things that we have. When x is equal to pi by 3, or when does this cos x is 1 by 2? Pi by 3. When this minus 1, it is pi. Okay. So now find f double dash x. F double dash x. So if we again differentiate this, this is what we get. And then substitute these points here. X is equal to pi by 3. F double dash pi by 3 is minus 3 root 2 by 2. What does it mean? Whenever f double dash at a is negative, we have maximum value. Okay. And f double dash pi is equal to 0. So because the f double dash is negative, yet pi x is equal to pi by 3, we have maximum value. F double dash pi is 0. Let us see whether f dash x changes sign or not. When x is slightly less than pi, f dash x is negative. What is happening? What is the direction of f dash x? F dash x, when x is less than pi, f dash x is negative. Okay. And then when x is slightly more than pi, f dash x is again negative. That means f dash x does not change sign as x passes through pi. It is continuing the same trend, that is f dash x is negative. So f of x is neither maximum nor minimum at x is equal to pi. This is from this last condition, that is 4a and 4b. From these two procedures, fourth principle of the procedure, that's what we arrive at. Next problem is, analyze the function f of x is equal to so on and so forth and classify the stationary points at maximum, minimum and points of inflection. So whenever we have a problem like this, first thing is find f dash x equal to 0. That's what we do here also. F dash x is 60x power 4 minus 180x cube plus 120x square equal to 0. X is equal to, if you take x square common, x is equal to 0, 1 point, and other roots are x is equal to 0, 1, 2. Again, find the maximum minimum points. Find f double dash x. This is 240x cube minus 540x square plus 240x. Substitute the points at x is equal to 0. F double dash is 0. So x is equal to 0, neither a point maximum nor minimum point. It's a point of inflection. At x is equal to 1, f double dash is negative, so it's a maximum value. The point of maximum value, and the maximum value of the function is, put this x is equal to 1 in this function, 60 minus 180 plus 120. Sorry, this is 12 minus 45 plus 40 plus 5. Value is 12. At x is equal to 2, if you find f double dash x, this is 240, it's a positive quantity. So at x is equal to 2, you have a minimum value. And what is the minimum value? Put this x is equal to 2 in the given function, you get this value. So in these points, then another thing we have used, that is stationary points. What we mean by stationary points? Whenever we equate this f dash x to 0 and find the values of x, these are called stationary points. They are called stationary points. Show that the right circular cylinder of given surface and maximum value is such that its height is equal to the diameter of the base. The right circular cylinder of given surface, problem may be, it might be like, show that this type of questions will not be there in the gate anyhow. For understanding, I am giving this problem to you. The right circular, the question may be, the surface of the right circular cylinder is maximum, so on and so forth. If the height is equal to diameter of the base or square of the diameter, or maybe half of the diameter, diameter cube, maybe options may be in different ways. So let R be the radius of the base and H be the height of the cylinder. The surface area is S is equal to 2 pi R H into 2 pi R square. So in a cylinder like this, we have 2 pi R H, and these two are circular ends. We have pi R square. So 2 into pi R square plus surface of the cylinder is 2 pi r h, and the volume you know that it is pi r square h, where v is the function of two variables r and h here. To express v in terms of one variable here, see, mind you, here two variable function, actually we have to deal with this problem in partial differentiation, but anyhow we can convert this into one variable problem. So if you convert into one variable problem, we can write v is equal to, from these two relations we can write v is equal to 1 by r2 sr minus pi r cube. So we want to find the maximum and minimum of this. So dv by dr is equal to 1 by 2 s minus 3 pi r square. For v to be maximum or minimum, dv by dr must be equal to 0, equated to 0. So what is r? Square root of s by 6 pi. So for maximum or minimum, to arrive at the conclusion, find the second derivative of d square v by dr square. So this is, s is a constant surface, surface is constant, so this becomes 0 minus 6 pi r. Here r is radius, it is always positive, it cannot be negative, and 6 pi is a positive constant, so it is always a negative 1. Minus 6 pi r, because r is always positive, it becomes always negative, so which is negative for r. So whenever d square v by dr square second derivative is negative, what we get? V is maximum for r is equal to square root of s by 6 pi. For 6 pi r square, which proves the required result. This is what we do in this. So under 5-6 problems are given for you as exercise problems. Okay, and this is about maximum, minima, and with this we conclude single variable calculus. That means your differentiation, integration, mean value theorems, maxima, minima, and all these things are completed. Now let's go to partial differentiation. Partial differentiation. Till now we have focused on functions with only one independent variable. Okay. Sorry. So just now we have seen that in the previous slide, the volume of a circular cylinder, V is equal to pi r square h. What we are doing here, what is r? Radius, and what is h? That is height of the cylinder. Say for example they are changing, r and h are changing variables. Now we want to find how this volume changes as we change r and h. So that means what happens, volume is a function of two variables now. One is radius and other is height. Simple example. Okay. Similarly, if you, most of your mechanical engineering students are there, if you consider the conduct of heat in a metal plate. Say for example, if I take a metal plate like this and it's heated, I start heating this body from this point. Okay. So the heat at this point will be maximum. As you go away from this point, the temperature changes. At this corner, the heat will be less. So what is happening? The heat is a function of this x and y variables. As you move away from the point, as you change the point, here the temperature is different, here the temperature is different, here the temperature is different. So what is changing? The temperature is changing with respect to x-axis and y-axis. So your temperature is a very good two variable function. So similarly, you can consider a cube and a metal cube and find I can discuss the same idea in three variables. So in most of the applications, in most of the real world problems, we come across functions with more than one independent variable. Say for example, if I take a fluid pipe here and the fluid is flowing through this pipe, right? At any point in this, fluid means it's a pipe with a three-dimensional body, right? So x-axis, y-axis and z-axis, you have three axes. So at any point, if you consider the fluid flow, if you find the velocity, that depends on, the velocity may be changing from this point to this point. So as you go around, velocity may change. So at this point, it depends on x, y, z. At this point, it x, y, z. So here also, that is also a function of three independent variables. So if u is equal to f of x1, x2, so on and so forth, x, then u is called a multivariable function with n independent variables. This is the basic idea. Anyhow, we restrict our discussion mostly to 2 and 3 variable functions, because in our discussion we don't go beyond that. The higher dimension your planar geometry or 3-dimensional geometry. So just like in a single variable case, we always discuss in interval AB. Y equal f of x is defined over a closed interval AB. That is the domain. Someone asked me what is a domain. In the example I said 1 to infinity, x is 1 to infinity. So it is on the real line because f of x is a one-dimensional function. What I mean is one-dimensional, one independent variable. That is along real line. So when we deal with 2 variables, x and y, what happens? That means you have one variable only x-axis. If you have 2 variables, 2 independent variables, you have x-axis and then y-axis. What is that? X and y-axis called coordinate system. That is xy plane. It's called xy plane. So how do we define the domain here in xy plane? It's not an interval. So then that's what we call it delta neighborhood of a point in a plane. We don't call it an interval here. We call a neighborhood here. Okay. So delta neighborhood of a point AB in xy plane is a square bounded by x is equal to a minus delta. I am marking this, observe the diagram with mark cursor. This is x is equal to a minus delta. This is x is equal to a plus delta. Y is equal to b minus delta. Y is equal to b plus delta. So these are the 4 lines. X is equal to a minus delta, a plus delta, y equal to b minus delta, and y is equal to b plus delta. I am sorry, this is b plus delta. Are 4 straight lines, and x lies between this and y lies between this. So the common area between all these lines, this one, this one, this one, and this one. The common area is a square here. So when we talk about 2 variable system, 2 variable function, the domain is a square, maybe a rectangle, depending on the problem. This is what we call a delta neighborhood. Sometimes the neighborhood may be an open disk also. Open disk, what we call open disk means, you know that disk is always circular in nature. Why we call this as disk is, it is a circular region in xy plane. This is our x-axis, y-axis, and draw a circle at center AB. Neighborhood of a point AB may also be defined as an open circular disk with center AB and radius delta, that is x minus a whole square plus y minus b whole square is less than delta square. Inside less than delta square means points lying inside the circle, that is the region. So when I define a 2 variable function on this domain, that means from the definition of domain, the function can take any point inside this circular region. Okay, this is what we mean by a domain here. In the earlier case, it can take any point from the square, and here it can take any point from the circular disk. Now, how we define the limits in this? In one variable case, we said x tends to a from the left or right, because we have only one variable x-axis. You cannot go like this because x can move along the real line only. It can take only real numbers. So x goes to a from the left or from the right. Only 2 options. But in 2 variable, what happens? Let us see. We use f of xy is said to have limit L as xy approaches AB, and it's denoted by limit xy tends to AB, f of xy is equal to L. If for given epsilon greater than 0, you can find a delta such that f of x minus L less than epsilon, in the neighborhood, so on and so forth. This is the similar sense as we defined limits for one variable thing. But the important thing is procedural point, there is a lot of changes there. We have to be very careful. Here, mind you, you have to be very careful. Why? Because the function appears to have a limit. By looking at the function, you say the limit exists. But sometimes it's not so. Be very careful. The limit of the function is said to exist only when the limit along any path in xy plane from xy to AB is same. Otherwise, the limit does not exist. The limit of the function is said to exist only when the limit along any path in xy plane connecting xy and AB is same. What is this path? What is this path? Let us see. Okay, we go to this path. First take it down. Again, I will let you, after the properties, I'll explain this. Let's see some of the properties. As xy tends to AB, limit f of xy is equal to L, limit of g of xy is equal to M. Then as xy tends to AB, limit of f of x plus or minus g of x is equal to L plus M. And the other things, limit of fx into dx is equal to L into M. Limit of f by g is equal to L by M, provided M not equal to 0. Okay. Now, as I said, the limit of the functions is said to exist only when the limit along any path is same. What I mean by this? Let's see this diagram. This is a bit very small diagram to accommodate time. See here, this is one point. This is another point. I can rather increase it. Okay. Yeah. So if this is a point, let us say AB, this is fixed point AB, this is XY. Now, the whole XY plane is your region. You can move any point, the domain, that means XY can take any point in this plane. And that is the case. This point XY can approach AB in how many ways? You can straight away come down like this along the straight line, joining these 2 points. That is one path. Okay. Otherwise, you can come like this as a parabola. You can come like this parabola. Otherwise, more simpler way, you can come like this, go like this, a more linear one. Or else, you can go like this, go like this. So this is AB, then come like this, or come like this, You can go from like this directly along straight line, along this, along this. These are the different paths. There may be still infinite number of paths. You can have something like this, you can something like this, so many curves, but we have to generalize these paths. So this is what I mean by different paths. So whatever path you take, whatever path you take, the limit must be same. The limit must be same. Then in such case, we say that the limit exists. So how do we evaluate the limit? What is the procedure to evaluate the limits? Limit f tends to first limit f of xy as x goes to a. This is xy, this is the fixed point AB. That means x goes to a and y goes to b. X goes to a and y goes to b. Or else you go like this, y goes to b and x goes to a. Second path. So otherwise, parabola, that means y is equal to, for n is equal to 2. If for n is equal to 1, we get y is equal to mx like this along the straight line. When n is equal to 2, we have parabola like this. For n is equal to 3, cubic polynomial. Like this, so many polynomials we can find n 3, 4, 5. We cannot do it for every polynomial, for every value of n. Basically, we do for these two things, and then y is equal to mx and y is equal to mx square. In all the 4 paths, the first, second, third, we have two things, y is equal to mx and y is equal to mx square. In all the 4 paths, the limit is same, then we say that the limit exists. If in any case, the limit, 2 limits are not equal, then limit does not exist. Let us see. Problems. F of xy is equal to y square minus x square plus y square. Find limit as xy goes to 0, 0. As what I said, xy tends to 0, 0 means x goes to 0, y goes to 0. Okay. As first, x goes to 0. If you put x goes to 0 in this limit, what happens? This is 0, this is 0. So what happens? Y square is 1. Okay, it is independent of y. You need not put limits. Then second case, first let y goes to 0 in this function. So when y goes to 0, this is 0, this is 0. What is remaining? Minus x square by x square. What is the limit? Minus 1. So what is the limit in the first case? 1. What is the limit in the second case? Minus 1. They are not equal. So limit does not exist. So take another example. Limit x goes to 1, y goes to 2, 2x square y by x square plus y square plus 1. First, limit x goes to 1, y goes to 2. Okay. Substitute y goes to 2 in this. what we get is limit x goes to 1, 4x square, and y goes to 2, 2 into 2x square plus x square plus 4 plus 1. This is what we get, 2 by 3. Now reverse these limits. Okay, limit. Here we have considered x goes to 1 and then y goes to 2. Now, first apply x goes to 1 here. Here first we have done y goes to 2. Then x goes to 1. Here x goes to 1 first and then y goes to 2. Substitute this thing. Then if you put x is equal to 1, 2 by y square plus 2. Again, if you put y is equal to 2, it is 2 by 3. See, in both the cases, the limit is 2 by 3. That's how we get. Now, f of xy is equal to x minus y by 2xy. So, if you, as limit x goes to 0, y goes to 0. What happens here? As first limit y goes to 0, f of xy, this is what we get. If you put y is equal to 0, x by 2x. X gets cancelled, limit x goes to 0, this is cancelling x by 1 by 2. And now change the limits. X goes to 0 and y goes to 0. And if you put x is equal to 0, this will be going, it will be cancelled. So what we have, minus y by y, limit y goes to 0, this is minus y. Then what are the limits? 1 by 2 and minus 1. Hence, the limit does not exist. Okay. So, that is about, and there are some problems in both the cases. These two limits are equal, and then y along y is equal to mx, it may fail. Sometimes, as y goes along y is equal to mx, also the same limit comes, and then along y is equal to mx square or x is equal to my square, the result fails. The limit is not the same. So we have to check those polynomials. Now, continuity. What is continuity here? A function f of xy is said to be continuous. The similar lines as we discussed earlier yesterday also. Limit must exist and limit must be equal to functional value. So a function f of xy is said to be continuous at AB if limit xy, limit f of xy is equal to the functional value at the given point AB. As x goes to A, y goes to B, limit of this function must be equal to f of AB. Discuss the continuity of f, which is defined as f of xy is equal to minus x by square root of x square plus y square when xy not equal to 0, xy not equal to 0 comma 0, and when xy is 0 0, the function value is given as 2. So limit x goes to 0 first. We have to find the limit, because limit of f of xy you have to find first. First, limit x goes to 0. What happens? When you put the limit x goes to 0, this function becomes 0. Okay. The second case, y goes to 0. Limit of f of xy, what happens? X by x square root of x square plus 0. Square root of x square is x cancels. Limit is 1. Here the limit is 0, it is 1. Limits are not the same, so limit does not exist. When the limit does not exist, there is no continuity, discontinuous function. Examine the continuity at the origin of the function defined, so on and so forth. So, limit x goes to 0, y goes to 0 first. If you put y is equal to 0, you get x square by x, limit x goes to 0. If you cancel x, limit x goes to 0, x is 0. Okay. If you change the limits now, limit y goes to 0 and then x goes to 0. Limit of y goes to 0. If you put x goes to 0, this becomes 0. Okay. So, 0. So, in these two cases, limits are same. Let us see, along the path y is equal to mx. I said no, y is equal to mx and y is equal to mx square, you have to check it. Along the path y is equal to mx. So, substitute this y is equal to mx in the given function. Then what happens? X square by square root of x square plus m square x square. And along y is equal to mx and x goes to 0. Then what happens to y? As x goes to 0, m into x also goes to 0. That means y also goes to 0. So x goes to 0, y goes to 0 is also achieved along y is equal to mx. So the condition now becomes x goes to 0, x square by x square plus m square x square. If you take this x square out, this is x square by x, that means x by square root of 1 plus m square, this is 0. This is also the same limit we have. Then next polynomial along y is equal to mx square. Substitute this. We get x square by x square plus m square x power 4. Okay. X square by x square plus m square x power 4 we get here. So if you take x square common, one x will be cancelled. Still square root of 1 plus m square x square will be there. So when you put x is equal to 0, again the limit becomes 0. So the fx is continuous. F of xy is continuous at 0, 0. Okay, is it clear? Next problem. Discuss continuity of the function 2xy by x square plus y square when xy not equal to 0, 0, 0 when xy is equal to 0. X goes to 0, y goes to 0. Then we put x equal, y goes to 0 first. I think there is some mistake in this. Okay. Then you, this is some mistake in typing here. Okay. First, when x goes to 0, the limit becomes 0. When y goes to 0 first, then also 0. Along y is equal to mx. Okay, is it correct? Continue along the line y is equal to mx, because along when you put x is equal to 0 or y is equal to 0, the function is having same limit, no problem. The problem comes with along y is equal to mx. When you substitute y is equal to mx in this function, this will be 2x 2m into x square by x square plus m square x square. Okay, and limit x goes to 0. So if you cancel x square throughout, you will be left with 2m by 1 plus m square. Do you have any term of x here? No. So x is not depending on x. Then what is m? What m is any parameter. As I said yesterday, it is any parameter, any arbitrary constant m. So if you change the value of m, the limit value changes. So if I take m is equal to 0, you get the same limit. If I put m is equal to 1, I get limit as 1. 2 into 1 by 1 plus 1, 2. If I get m is equal to 10, 20 by 101. So how many limits we are having? Infinite. It depends on the value of m. So unique limit is not achieved. So here the limit does not exist. When the limit does not exist, the other two conditions are given. Here the limit is 0, here the limit is 0. But here it's not so. 2m by 1 plus m square. So the limit does not exist, so the function is not continuous. Another example. So take this function x cube plus 3 by 2x plus y as xy tends to 2, 3. First take x goes to 2, y goes to 3. Okay, like this. The limit is 42. Change the order of limits. That means x goes to 2 first, y goes to 3. Then the limit is also 42. But what is the functional value here? But the continuity limit must be equal to function value. But what is the function value here? It is 10. The limit value is 42. They are not equal. So hence from equations 1, 2, 1, there exists limit of f of xy is equal to 42, which is not equal to 10, which is the function value of 2, 3. So the function is discontinuous. So this is the type of problems that we come across in continuity and differentiability. Hope you're understanding, right? So next one is differentiability, partial differentiation. Let u of x, y, z be a 3-variable function. If you keep y and z as constants, treat them as constants. They are not constants, but fix them and vary x, change x. Then derivative of u with respect to x is called partial derivative of u, denoted by dou u by dou x. So dou u by dou x is limit h goes to 0, f of x plus h minus yz minus f of x by z by h. These things are almost all similar definitions as in differential calculus. Similarly, partial derivatives with respect to y and z are also defined and are denoted by dou u by dou y and dou u by dou z respectively. Higher order partial derivatives. The higher order partial derivatives of u is equal to f of x, y, z are obtained by successive differentiation. That is, dou square u by dou x square. The second order derivatives we have dou square u by dou x square, dou square u by dou x dou y, dou square u by dou y square, dou square u by dou y dou x. We have 4 second order derivatives. Okay. When you have only 2 variables, right? If I can say only 2 variables. So dou square u by dou x square is dou by dou x of dou u by dou x, dou square u by dou x dou y, dou by dou x of dou u by dou y, and dou square dou y square is dou by dou y of dou u by dou y, and so on and so forth. Mixed partial derivative, this dou square u by dou y dou x and dou square, this one, dou square u by dou x, they are called mixed partial derivatives. This one and this one. Mixed partial derivatives, dou square u by dou x, sorry, this is not correct, this is mistake here. Mixed partial derivatives are equal if the derivatives involved are continuous. That means, I'm sorry, this is a mistake, I will correct it. Okay, these two things. Mixed derivative means dou square u by dou x dou y and dou square u by dou y dou x are equal if the derivatives involved are continuous. Then this very important idea in partial differentiation is total derivative, which is a new thing which we don't have in ordinary one variable calculus. We have in total derivative because this u changes with respect to x, u changes with respect to y, u changes with respect to z. So, with respect to x, you have dou u by dou x. With respect to y, you have dou u by dou y. With respect to z, you have dou u by dou z. Okay. So, what happens? And while finding dou u by dou x, we are assuming y and z are constants, as I said here. Keeping y and z. Similarly, when I am finding dou u by dou y, I keep x and z constant. When I find dou u by dou z, I keep x and y constant, right? So, when none of the variables is fixed, that means all are changing. X is changing, y is changing, z is changing. What is the cumulative derivative, cumulative impact on the derivative of u? This is what we discuss here. What is that for total derivative? Is defined as df, that is dou u by dou x into dx, dou u by dou y into dy, dou u by dou z into dz. Then chain rule. Okay. If u is equal to f of x, y, z, and x, y, z are again functions of t, mind you, this concept generally comes in mostly in parametric form of curves. Actually, we have seen x is equal to x of t and y is equal to y of t, parametric form of curves. And we have studied in arc lengths, right? Okay. So x, y, z are functions of t. Then f can be treated as a function. So when you substitute x's and y and x, y, z are functions of t, put them in this here, what happens? F becomes a function of t. Then the derivative of u with respect to t is called total derivative and is defined by chain rule. Du by dt is dou u by dou x, dx by dt, dou u by dou y, dy by dt plus dou u by dou z, dz by dt. This is called chain rule. Let us see some problems. Find the total derivative of u is equal to x square minus y square, where x is equal to e power t cos t, y is equal to e power t sin t, and t is equal to 0. So the chain rule is, because here u is a function of x and y, but x and y are again functions of t. So chain rule. This is what we study here. U is equal to f of x, y, z, x, y are again functions of t. Then we apply chain rule. So du by dt is equal to dou u by dou x into dx by dt, dou u by dou y into dy by dt. So what is du by dt? So dou u by dou x is x square, 2x, derivative of u with respect to x, with respect to x is 2x, and dx by dt, x is e power t cos t. So dx by dt is uv, e power t into derivative of cos t minus sin t, cos t into derivative of e power t is e power t cos t. Similarly, dou u by dou t, dou u by dou y, what is dou u by dou y? Minus 2y into dy by dt, e power t into derivative of sin t cos t plus sin t into e power t. So this is our du by dt total derivative using chain rule. What we want at t is equal to 0. If we put t is equal to 0 in this, the value is sin t becomes 0, e power 2t becomes 1, cos t becomes 1. So if you simplify this, you get this as value is 2. Find du by dt of u is equal to log ln x plus y plus z, where x is equal to e power minus t, y is equal to sin t, and z is equal to cos t. So du by dt is equal to dou u by dou x, 1 by x plus y plus z into dx by dt. Dx by dt is e power minus t into minus 1 plus dou u by dou y is ln of x by the derivative of this is 1 by x plus y plus z into dy by dt cos t. Dou u by dou x 1 by x plus y plus z into dz by dt is cos t of derivative of cos t is minus sin t. This is what we get. Find du by dt for the following function x u is equal to sine of x by y. X is equal to e power t, y is equal to t square. U is equal to sine of x by y. So du by dt is dou u by dou x and dx by dt. Dou x by dou u by dou y into dy by dt. This is dou u by dou y into dy by dt. So dou u by dou x is, first thing is cos x by y. Derivative of this with respect to x. Cos x by y into x by y. Derivative with respect to x is 1 by y. What is dx by dt? E power t. Plus dou u by dou y. Cos of x by y again. X is a constant minus. And what is derivative of 1 by y with respect to y? Minus 1 by y square. And dy by dt is 2t. Okay. So simplify this. That's what we get. Then u is equal to x into log x by, where x cube plus y cube plus 3xy is equal to 1. Find du by dx. Find du by dx. So x cube plus y cube plus 3xy is equal to 1. So du by dx is dou u by dou x. Okay. Into dx by dx. Here it is dx by dt because x is a function of t. So you are getting du by dt. When you want du by dx, that means in place of t, if you take what happens? Dou u by dou x into dx by dx, that is 1. Dou u by dou y, dy by dx. So that is what I am applying here. Okay. So x cube plus y cube plus 3xy minus 1 is equal to f of xy is an implicit function. We have to find dy by dx from this. So fx is dy by dx, x implicit function, differentiation of implicit function we have discussed earlier. Dy by dx is equal to minus fx by fy. So fx is 3x square plus 3y, fy is 3y square plus 3x. This is what happens. So now we put these things in given formula du by dx. Du by dx is equal to dou u by dou x plus dou u by dou y into dy by dx. So what is dou u by dou x? X in this one, dou u by dou x, uv formula, x into derivative of log xy. That means derivative of x is 1 into log xy plus x into 1 by xy into y, 1 by x, that becomes 1. So du by dx is dou u by dou x is, this is 1 plus log xy. Dou u by dou y is x by y into dy by dx. This is what happens. If u is equal to log of x cube plus y plus z cube minus 3xyz, find dou by dou x of dou by plus dou by dou y plus dou by dou z whole square of u is equal to so on and so forth. U is equal to log of x cube plus y cube plus z cube minus 3xyz. Dou u by dou x by keeping y and z are as constants. Dou u by dou x becomes 1 by first derivative of logarithmic function 1 by x cube plus y cube plus z cube minus 3xyz, and derivative of this with respect to x is 3x square minus 3yz. Dou u by dou y, similarly find this. So now dou u by dou x plus dou u by dou y plus dou u by dou z, we add these three things, that what we get. This is what we get. So remaining way, dou u by dou x whole square, this into this, you can find similarly, because I cannot explain all problems and just skipping down 1 or 2 problems. You can just go through these problems. Okay. So just go through the problems. If you have doubts, you can ask me. Certain problems are given to you. So differentiation of implicit functions, we have discussed this already. An implicit function of x and y is the form f of xy is equal to 0, which cannot be solved for one variable in terms of the other explicitly. That means f of xy is equal to 0. So if you cannot solve x in terms of y, or you cannot write y in terms of x, then this f of xy is equal to 0 is called an implicit function. That means, say for example, this function, if you take y power x power y is equal to sin x. What is x? Sin inverse of what all you can say is x is equal to sin inverse of this thing. But x is equal to, can we explain x only in terms of y? No. because y power x by y is there. You cannot do it. So it's an implicit function. In such case, we want to find the derivative using partial derivatives. Dy by dx is equal to minus dou f by dou x by dou f by dou y. So for example, for this problem, take logarithm ln on both sides. So it becomes x power y ln y is equal to ln sin x. So if you put x power y is equal to z, then ln z, again take logarithm for this. Ln z is y log x. Then if you differentiate this with respect to x, this with respect to x, ln z derivative is 1 by z into dou z by dou x is equal to y by x. Implies that zx is yz by x. Okay. What is z? X power y. If you put it here, y into x power y minus 1. And again differentiate this with respect to y. This with respect to y. Ln z is 1 by z into dou z by dou y is equal to y log x. Derivative with respect to y is ln x. Okay. Implies that zy is equal to z log x or x power y ln x. Now consider f of xy is equal to okay. Yeah. So 1 by z dou z by dou y is equal to ln x implies zy is equal to z ln x or x power y ln x. Now consider f of xy is equal to this one, x power y ln y minus log sin x. So what all we have till now is all required results we have completed. Now f of xy is equal to x power y ln y minus log sin x. So dou f by dou x is dou by dou x of x power y ln y minus derivative of this is 1 by sin x into cos x. And dou f by dou y is partial derivative of x power y with respect to y into ln y. So this is what we get. So dy by dx is this by this. Okay. F of xy is equal to x into sin x minus y minus x plus y. So dou f by dou x is sin x minus y, derivative of x is 1, plus x into cos x minus y minus 1. Dou f by dou y is, here x is there, and so derivative of this only, so cos of x minus y into minus 1 minus 1. So dy by dx is minus dou f by dou x by minus dou f by dou y. This is what we get. This is how we find derivatives for the implicit functions. Then homogeneous function. What is the homogeneous function? A polynomial in x and y is said to be homogeneous if all the terms are of the same degree. What do you mean by this? So you can put it mathematically as f of lambda x, lambda y is equal to lambda power n into f of xy. Okay. Then f of xy is said to be a homogeneous function of degree n, and it can be this f of xy for testing purpose. F of xy, if you can write x power n into phi of y by x or y power n into f of phi of x by y, then we say that function is a homogeneous function of degree n. See, let us see. There are certain problems. Find the degree of this polynomial. Say for example, this is a polynomial in x and y. What is the degree of the polynomial? So 3x square minus 2xy plus 15y square. So that means to know the degree of the polynomial, you have to first write this function either this form or this form. So take whatever maximum you can take out common, that is x square. If you take x square common, what happens? 3 minus 2 into y by x plus 15 into y by x whole square. So this is a function of y by x. So this is x squared into phi of y by x. That means this is in this form. So f of xy is a homogeneous function in x and y with degree 2. Let us say E is equal to sine of square root of x minus square root of y by square root of x plus square root of y. So if you take root x common, x power 1 by 2, then becomes 1 minus y by x under root by numerator also if you take root x common, 1 plus square root of 1 by x. So this is a function of y by x. But what is x power here? X by x root x get cancelled, we get x power 0. So u is equal to sine of square root of x minus square root of y by square root of plus x plus square root of y is a homogeneous function, there is no doubt, but degree of the polynomial is 2. Degree of the homogeneous function is 2. Then we have an important theorem here, what we call Euler's theorem. If f is a homogeneous function of xy of degree n, then x dou f by dou x plus y dou f by dou y is equal to n into f. This is a very, very important theorem. Straight questions may be asked on this. For example, u is equal to log of x square plus y square by x plus y. Find x dou u by dou x, y by dou x. Clearly, this is equal to n into f. Okay. So x square plus y square by x by e. From this, you can write x square plus y square by x plus y as e power u. Then call this as f. Okay. Then by Euler's theorem, x ux plus y uy is equal to u, and then you apply Euler's theorem not for u, for f. Okay. So when you apply this, what happens? X into dou f by dou x plus y into dou f by dou y is equal to n into f. So where f is equal to e power u. What is dou f by dou x? E power u into dou e by dou x. Dou f by dou y is e power u into dou e by dou y. So x fx plus y fy becomes x ux eu plus y uy eu is equal to f. N into f is this thing. Okay. This is how we do this problem. Because then what about n here? You can ask me what happens to n. N, what is n? Degree of the homogeneous function. What is the degree of the homogeneous function here? X square, if you take common, 1 plus y square by x square by, if I take x here, x square by x. So x remains. So degree is 1. Okay. So nf, here it should be nf, but n is 1, so f is there. Find the value of x dou e by dou x plus y dou e by dou y plus z dou e by dou z if u is equal to so and so. So as we did in the last problem, consider cos u. Cos u is x cube plus y cube plus z cube by ax plus by plus cz. Call that as f. So our f is cos u, which is equal to x cube plus y cube plus z cube by ax plus by plus cz. And what is the degree of the polynomial here? 2. Because if you take x square common, it is a function of y by x and z by x. Here also x take out x here. Numerator x square, x cube we have taken, and in denominator we have taken x cube by x, we get x square. So degree is 2. So extending this Euler's theorem to 3 variable, x dou f by dou x plus y dou f by dou y plus z dou f by dou z is equal to 2 degree n into f. So dou f by dou x, find out this. This is what we get. So dou f by dou y, dou f by dou y, dou f by dou z. So if you put these things in this formula, x ux plus y uy plus u equal minus 2 cot u. So we have one more problem on this Euler's theorem. So here is a function of 0, degree of 0 here. So x dou e by dou x plus y dou e by dou y plus z dou e by dou x becomes 0 into u, which is 0 straight away. It is a direct question. Just looking at the problem, you can say degree is 0. So some more problems are there here. Please go through, and if you have any doubts, you can ask me, you can put a mail. Okay, I'll explain. Then one more important thing, very frequently also we are getting some questions on this in Jacobians. Maybe questions may be like this, on the properties of Jacobians. Let us see what is Jacobian first. Let u of xyz and v of xyz be two functions of, let us say, in three independent variables, x, y, and z. I'm sorry here, x, y, and z. The Jacobian of u and v and w with respect to x, y, z is denoted by j of u, v, w by x, y, z, or dou of u, v, w by. Either notation you can follow. You can write like this, or you can write like this. Both mean the same. So Jacobian of how we read this is Jacobian u, v, w with respect to x, y, z. It is given by determinant dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, dou w by dou z. Properties. If this is Jacobian, then Jacobian star is dou x. Reverse this. U, say, I'm sorry, this is j actually. J is dou u by dou xy, and j star is dou xy by dou u by. Then j into j star is 1. If u, v are functions of rs, and rs are again functions of xy. Read again. U, v are functions of rs are again functions of xy. Then dou u, v by dou xy. Then you are neglecting this r and s here. Let us see. See, observe. Then directly you are finding out the Jacobian of u, v with respect to xy. That is given by dou u, v by dou rs. The Jacobian of these two first into Jacobian of these two. Sort of chain rule in Jacobians. Okay. So if x is equal to r cos theta and y is equal to r sin theta, then if you put this, if you use this, becomes in place of u we have x, in place of v we have y, in place of x we have r and y, and x and y we have r and theta. Then you find the Jacobian, that value is r. And if x is equal to r cos theta and y is equal to r sin theta, z is equal to 0, then we have to understand this polar coordinates and cylindrical coordinates once. What are these polar coordinates and cylindrical coordinates? You know, polar coordinate system is two-dimensional system. This polar coordinate system is a two-dimensional system, whereas cylindrical and spherical coordinate systems are three-dimensional systems. In polar two-dimensional systems, what are r and theta? If you take a point in coordinate plane, if you take a point, you join this point with the origin, you get a straight line like this. And what the length of this segment that you consider, that is r, and the angle it makes with the x-axis, positive x-axis, that is theta. So if that is the case, then x is equal to r cos theta, y is equal to r sin theta. It is very much familiar to you. Then Jacobian is r. When x is equal to r cos theta, y is equal to r sin theta, and z is equal to z, a cylindrical coordinate system, then Jacobian is r. Then what is this cylindrical coordinate system? We'll see what we mean by that. So you have x-axis, y-axis, and z-axis. When you consider right circular cylinder, that means what is right circular cylinder? What is the basis of that circular cylinder? A right circular cylinder is generated from a circle in xy plane. Say for example, if I have a circle like this in xy plane, okay, if I extend the circle along z-axis, that will be the height of the cylinder. Say for example, the best example, you take all the girl students, you take the bangles, put the bangle on the table, that is one circle, and put all these bangles one over the other, then what you get? All the bangles like this, that's a cylinder. What is the basic thing? Circle. And circle over circle, circle over circle, like this, we are getting a circular cylinder. On the cylinder, if you cut the cylinder at any point, again you will have a circle. So Z is nothing but height of the cylinder. Z is nothing but height of the cylinder. If you put Z is equal to 0, that means cylinder like this, let us say this is a cylinder, this is the height, Z is Z, and If we make this z is equal to 0, what happens? In xy plane, you have a circle. What are the parameter representation of r polar form of a circle? X is equal to r cos theta, y is equal to r sin theta, so that x square plus y square is equal to r square cos square theta plus r square sin square theta is equal to r square gives you a circle. Generated from a circle in xy plane. That's why the third variable z is always kept as z. Okay, so that's what we mean by r cos theta, r sin theta, and z, cylindrical coordinate system. So when we have a coordinate system is changed from cylindrical coordinate, I mean Cartesian coordinates to cylindrical coordinates, then the Jacobian is given by r. Then one more three-dimensional system, that is spherical coordinate system. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta, dou x y z by dou r theta phi is r square sin theta. Particularly for ECE students, these coordinate systems, polar, cylindrical, and spherical coordinate systems are very important spatial system we use in terms of r theta and phi more than anyone else. I think you must be well aware of these facts, but anyhow, just be very careful with these things. So this is a spherical coordinate system. Then what is spherical coordinate system? Let us see. So this is a spherical coordinate system. Okay. Okay. So this is the x-axis, y-axis, z-axis. If I take a point P, join this with the origin pole. Okay. P in the space. So this is my coordinate system. I take a point here. I take a point like join this here. Okay. This is my P. Then angle made by this positive z-axis. This angle. This is theta. This is what my azimuthal angle. Azimuthal angle. This is theta. Then if you take the projection of P in xy plane, let this be L. Okay. Join this. Right? Then the angle made by this with positive x-axis, this is called phi. This is called phi. Then this point can be expressed as r cos theta from this, and y is r sin theta sin phi, and x is equal to r sin theta sin phi. This is cylindrical coordinate system. If you completely rotate these things, but what are the limits of this r theta and phi? R changes from 0 to whatever you fix it, and when theta changes from 0 to pi completely, and this phi changes 0 to 2 pi, then this point generates the complete sphere. And the point completely generates the sphere. Okay. So as theta goes from 0 to pi and phi 0 to pi, phi from 0 to pi means xy plane like this circle is formed. Okay. So that's how spheres are formed. That's why this system is called spherical coordinate system. This is what happens. So this is theta, this is phi. So when this phi rotates 2 pi, so this circle we get. When theta changes 0 to pi, okay, this complete semi-sphere, and then this semi-sphere rotated by 2 pi, we get complete sphere. This is what we have to understand from spherical coordinate system. So when we have a spherical change of coordinate system, Cartesian coordinate to spherical coordinate system, then your Jacobian becomes r square sin theta. This is a very important idea in multiple integrals also. Okay. So find the Jacobian when x is equal to e power u cos v, y is equal to e power u sin v. So dou xy by dou u is equal to dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. Find dou x by dou u, e power u cos v, dou x by dou v is minus e power u sin v, dou y by dou u, and dou y by dou v. Put it here. This is Jacobian. Evaluate Jacobian x by z. So dou u by So do v by do xyz, this is the expression we have, and from the given functions u is equal to do u by do x is by z, do u by do y is z by x, so on and so forth. So if you put these things and find the determinant, that is your Jacobian. So u is equal to 2xy, we have taken a transformation here, see. U is equal to xy, v is equal to x square minus y square, x is equal to r cos theta, y is equal to r sin theta. Then find those Jacobian of u with respect to r and theta. I said no, u, v are functions of xy, but x and y are functions of r and theta. But what we are asking the Jacobian of uv with respect to directly in terms of r and theta. So that means we have to use the chain rule. So do uv by do r theta is equal to j uv by do jxy into jxy by do r theta. So first we have to find Jacobian of uv with respect to xy, j uv by do jxy. So this is 4r square. Then jxy by r theta. This is what we get. So j uv by r theta is j u v x y by j x y by r theta. This is what we do. So what is the importance of this Jacobian then? Jacobian, we have direct problems like this, finding the Jacobians. Then once you find the Jacobian, what is the importance of Jacobian? When I give you two functions f of xy and g of xy, how do you say whether they are independent or not? Independent or dependent? What do you mean by independent? Say for example, y is equal to x is a straight line. Y is equal to x, another straight line. They are dependent or independent? They are dependent. Why? Y is equal to x and y is equal to 2x. Y is equal to 2x can be expressed in terms of the first function. They are linear and parallel lines. So they are dependent. So how do you test the functional dependence or functional independence? So for example, e power x and e power 2x, they are independent. One cannot be derived from the other thing. The function u of x, f of x y and v is equal to g of x y are said to be functionally dependent on one another if j is equal to do uv by do xy is equal to 0. This is a very, very, very important result. Maybe direct questions may be from this. Maybe functions may be like this given to you. They are independent or not. You may ask they are dependent, independent. We cannot say other functionally something maybe some other third option may be there. We have to check whether the functions are dependent or not. For that we have to find the Jacobian. Do u by do xy. Do u by do x e power x sin y. Do u by do y is e power x cos y. Do vx. Do v by do x, that is e power x cos y. Do v by do y is this thing. So if you find the determinant e power minus 2x into sin square plus cos square, that is e power minus 2x, which is not equal to 0. Because it is not equal to 0, they are functionally independent. If they are 0, they are functionally dependent. X into u is equal to x into square root of 1 minus y square, y is equal to square root of 1 minus x square, y into square root of 1 minus x square, v is equal to sin inverse x plus sin inverse y are functionally dependent or not. You have to check whether these two functions are independent or not. So this is u, this is v. Find the Jacobian. So do u by do x, this one, do u by do y, do u by do x, do u by do y. So if you find the Jacobian, it is 0. See, the terms are so complicated, but finally Jacobian becomes 0. As a result, we are getting it is functionally dependent. Okay. So another function like this you can go through. In 3 variables you can practice it. Now, Taylor's theorem function for 2 variables. We have done it for 1 variable. This morning also we have discussed it, but now it is for 2 variables. Let f of x be a function of 2 variables. Then the Taylor series expansion about x is equal to j and y is equal to b is f of x plus h, y plus k is equal to f of xy plus h into fx, so on and so forth. So Maclaurin's theorem for function of 2 variables, if you take this a, b as 0, as I said earlier in the morning, then f of 0, 0 plus h into dou f by dou x 0, 0, y into dou f by 0, 0, so on and so forth. This is Maclaurin's theorem for two variable functions. Okay. So expand f of xy is equal to e power y log 1 plus x in powers of x and y using Maclaurin series. So what we have to find? To find the Maclaurin series of the function, we have to find f of 0, 0. You have to find dou f by dou x at 0, 0, dou f by dou y at 0, 0, so on and so forth. Okay. So this is your function. So first thing is f of 0, 0 we need. F of 0, 0, put x is equal to 0, y is equal to 0, log 1 becomes 0. So this is, I'm sorry, this is 0. This is 0. Some mistake here. Must be 0. Okay. So dou f by dou x is e power y by log 1 plus x. Dou f by means e power y into derivative of log 1 plus x is 1 by 1 plus x. You put 0 and 0, you get 1. Dou fy by dou y. So log 1 plus x is a function of x. So derivative of e power y is e power y into log 1 plus x. When you put y is equal to 0, x is equal to 0, log 1 becomes 0. Then dou square f by dou x dou y. So once derivative with respect to y, once with respect to x, so e power y by 1 plus x. If you put 0, x is equal to 0, y is equal to 0, it is 1. Similarly, dou square f by dou x square. Dou f by dou x is this one. Again, if you differentiate this, minus e power by 1 plus x whole square. If you put x is equal to 0, y is equal to 0, it is minus 1. Like this, you find the other partial derivatives also. And this is Maclaurin series expansion. Formula f of 0, 0 plus x into dou f by dou x 0, 0, y into dou f by dou y 0, 0, so on and so forth. If you put these things, we get the given expansion. Given f of xy is equal to e power xy, a Taylor series, we get f of x naught, y naught plus x minus x naught, f of x minus so on and so forth. This is Taylor series expansion because we need the expansion about 1 and 1. So dou f by dou x, dou f by dou y, dou square f by dou x square, dou square f by dou y square, dou square f by dou y square, so on and so forth. You find all these different partial derivatives. Substitute this point 1 comma 1, you get these things. Then you get this thing. Similarly, we have another problem. Taylor series expansion of these two functions in like this. Okay. And then maxima minima of functions of two variables. We have seen maxima function of one variable. Now we see maxima minima of function of two variables. What happens is, let f of xy be a function of two variables x and y. Let x is equal to a, y is equal to b. F of x is to have a maximum or a minimum value if f of ab is greater than, that means if f of ab is greater than f of a plus h, f of b plus k, then f of ab is maximum. And if f of ab is less than f of a plus h, b plus k for any h and k are any small values. That means, as I said, in a small neighborhood, if f of ab is having highest value, then we call maximum. If it is going up like this, as I said this morning. So the necessary conditions. Then how to find the maximum minimum points? Procedure we have seen in the morning for one variable functions. Now it is two variable functions. Again, it goes in the very much similar lines. Necessary conditions for f of xy to have a maximum or minimum at ab are dou f by dou x at ab is equal to 0, dou f by dou y at ab is equal to 0. So the sufficient conditions are dou f by dou x at ab is equal to 0, dou f by dou y at ab is equal to 0, and let dou square by dou x square at ab is equal to L, dou square by dou x dou y at m is m, dou square by dou y square is n. Okay. So the first test is this one. When you equate the first partial derivatives dou f by dou x and dou f by dou y equal to 0, we get the points. You have to solve them. You will get x and y. So f of ab is maximum whenever L n minus m square is greater than 0, where L is dou square by dou x square of the function at ab. M is dou square f by dou x dou y at ab. N is dou square by dou I square of F at AB. And F is maximum if Ln minus M square is greater than 0 and L less than 0. F of AB is minimum if Ln minus M square is greater than 0 and L greater than 0. See, the first one is common. Once Ln minus M square is greater than 0, then you have to check L, whether L is less than 0, L is greater than 0. Okay. If L is less than 0, it is maximum. If L is greater than 0, it is minimum. And F of AB is not an extreme value if Ln minus M square is less than 0. And Ln minus M square is 0 if then F of xy fails to have a maximum or minimum value. It needs further investigation. That means with the information available, we cannot judge whether the function has a minimum value or maximum value. Stationary value. F of AB is said to be a stationary value of F of xy if dou F by dou x at AB is 0, dou F by dou y at AB is 0. That means this condition. So at AB, if the point AB, if dou F by dou x and dou F by dou y are equal, then AB is called a stationary point. So the other way, question may be asked, function of F of xy is given to you, find the stationary points of F of xy. Find stationary points of F of xy. For that, what you have to do, find dou F by dou x equated to 0, find dou F by dou y equated to 0, solve these two equations, you will get those values of x and y for which these conditions are satisfied. And those points are called stationary points. So these are stationary points, but then from these stationary points we are finding out whether they are maximum or minimum points. Okay. So that means every extreme value is stationary value, but the converse need not be true. If this happens, if F is maximum, Ln minus M square greater than 0, L less than 0 or greater than 0, that means X maximum or minimum point. Obviously, this is stationary point. But every stationary point need not be extreme value. Why? This is happened. This is true. But what happens is, if Ln minus M square is equal to 0, neither maximum nor minimum. So that means every stationary point cannot be a maximum extreme point, but every extreme point is a stationary point. This is a very important, the last statement is a very, very important statement. Working rule to find the maximum or minimum values of F of xy. So find dou F by dou x, dou F by dou y, equate them to 0, solve the equations for x and y, let A1 be 1, A2 be 2, so on and so forth, with a pace of values such that dou F by dou x is equal to 0 and dou F by dou y is equal to 0. Then find L, that is dou square F by dou x square, M, dou square F by dou x dy, and N is equal to dou square F by dou y square. And substitute these points in this. So if Ln minus M square is greater than 0 and L is equal L less than 0 for A1 B1. For A1 B1, if Ln minus M square is greater than 0 and L is less than 0, then A1 B1 is a point of maximum value. And F of A1 B1 gives the maximum value. If Ln minus M square is greater than 0 and L is greater than 0 at A1 B1, then A1 B1 gives the minimum value. If Ln minus M square is less than 0 at A1 B1, then F of A1 B1 is not an extreme value. There is neither maximum or nor minimum value at A1 B1. In this case, A1 B1 is called a saddle point. In this case, A1 B1 is called a saddle point. Lastly, if Ln minus M square is 0 at A1 B1, no conclusion. The information is not sufficient, and we need further investigation for the maximum and minimum of the function. So, like this, for every point you have to check these conditions. A1, B1, we have tested this condition. Again, A2, B2, we have tested this condition. Sometimes we may have more than one maximum and minimum. Find the maximum values of x cubed plus 3x square minus 15x square minus 15y square plus 72x. The first step is find dou F by dou x, dou F by dou y, equate them to 0. Okay. So when you equate them to 0, what happens? You get 6y into x minus 5 is equal to 0. And if you equate dou f by dou y is equal to 0, y is equal to, so this same thing, okay, y is equal to 0 or x is equal to 5. If you equate dou f by dou x is equal to 0. And then dou f by dou y is, so if you put these points here, you get the other points also. X is equal to 5, y is equal to, then other, when y is equal to 0, and you get x is equal to 5. And these values, y is equal to 0 and x is equal to 6.4, and x is equal to 5 and y is equal to plus or minus 1. These are the points we have. Okay. X is equal to 5, y is equal to 1, x is equal to 5, y is equal to minus 1. Other points we have. So then ln minus m square. Then find ln minus m square. L is dou square f by dou x square, 6x minus 30, that's 6 into x minus 5. M is dou square f by dou x dou y, that is 6y. N is dou square f by dou y square, that is 6 into x minus 5. So now, yet the first point 40, ln minus m square, that is delta, is greater than 0. At B, 6, 0, delta is greater than 0. At this point 5, 1 is less than 0. At D is less than 0. What is the condition we have? Ln minus m square greater than 0. This is and then we have to check for L less than 0 or greater than 0. So at A and B, this 40 and 60, this delta is greater than 0. That means as A and B are points of extreme values for f, while C and D are saddle points. What is a saddle point? Whenever ln minus m point. Okay, so that means C and D are saddle points. We have nothing to do with this. Now we concentrate on ln A and B, for which this ln minus m square is positive. A is the point maximum for, because f dash is at L is greater than 0. B is the point of minimum, because L is 6 into x minus 5. We put the point is less than 0. We have extreme value, maximum value here. And whenever it's greater than 0, we get L minus m square greater than 0, L greater than 0, minimum value. So, whenever at A and B, this delta is greater than 0, and at A, xy plus a cube by x plus a cube by y. Again, first step is to find dou f by dou x, that is y minus a cube by x square, dou f by dou y, x minus a cube by y square. Second order derivatives also find dou square f by dou x square is 2a cube by x cube, dou square f by dou y square is 2y cube by y cube, and dou square f by dou x dou y is 1. The condition for f of xy to have minimum or maximum extreme values is necessary condition. Dou f by dou x is equal to 0 is equal to dou f by dou y. So if we equate them, y is equal to a cube by x square and x is equal to a cube by y square. So if you solve these two things, that means if you substitute this x here or y here, then we get y into y cube minus a cube is equal to 0. So y is equal to 0 or y is equal to a are the clear solutions. Now when y is equal to 0, what happens to x? Infinity. Okay, it is not possible. So when y is equal to 0, what happens? Y is equal to a. When y is equal to 0, x becomes infinity. It's not possible. Y is equal to a, x becomes a cube by a square, so x becomes a. So point is a comma a. So what is So F has a extreme maximum or minimum value at AA. Now we have to find what is maximum or minimum. For that you have to find the other test, that means ln minus m square. Ln minus m square is ln is at the point a comma a, L is dou square by dou x square is 2, m is 1 and n is 2. So ln minus m square is 2 into 2, 4 minus 1, that is 3, is clearly greater than 0. And what is L? It is also greater than 0. So f of x, whenever ln minus m square greater than 0, L greater than 0, f has minimum at a comma a. And what is the minimum value? Substitute the point in f, 3a square. That is minimum value. Investigate the maximum and minima if any of the function f of x is equal to x cube y square into 1 minus x minus y. So f of xy is this, dou f by dou x, find this x square y square into 3 minus 4x minus 3y. Dou f by dou y is x cube y into so on and so forth. Dou square f by dou x square, this one. M is dou square f by dou x square. Find this, n, so on and so forth. We get all these things by simply differentiating the function. So for the maxima or minima, dou f by dou x must be equal to dou f by dou y. So these things must be equal to 0. So x square y square into 3 minus 4x minus 3y is equal to 0, or x cube y into 2 minus 2x minus 3y is equal to 0. So clearly x is equal to 0, y is equal to 0 is solution in both the equations. And if you equate this, 3 minus 4x minus 3y is equal to 0. So we get from this 2 minus 2x minus 3y is equal to 0. So what are different points, different combinations we have? X is equal to 0, y is equal to 0, one pair. And then x is equal to 0, y becomes 1. Okay. And from this also, when y is equal to 0, x becomes 1. So otherwise, x and y, if you solve these things, these 2 points, 1 by 2 and 1 by 3. So there are different combinations, there are different points we have. So then we have to find which of these points gives a maximum or minimum value. So reasonable thing is we have to find ln minus m square first at different points. At all these points except 1 by 2, 1 by 3, ln minus m square is 0. That is no extreme value at 1, 2. And L is less than 0 as a point of maximum value. Okay. At 1 by 2. And that means at all these points, ln minus m square is equal to 0. But at this point, what is happening? If you find ln minus m square, this is 1 by 9.64, this is greater than 0. And also calculate L at this point, it is less than 0. So ln minus m square greater than 0, L less than 0, that means we get at this point a maximum value of the function, and the value of the function is obtained by substituting this point in the given function. Okay, that's how we do this. Find the positive numbers whose sum is 100 and whose product is maximum. Let us say x, y, z are the points. So the sum is 100, x plus y plus z is equal to 100, and the product is maximum, f of x, y, z. So this I want to be maximum. Okay. So you can write this as x, y, z in terms of, you can convert z is equal to 100 minus x minus y. Z is equal to 100 minus x minus y. You substitute this, then f of xy becomes xy into z. That is 100 minus x minus y, or k minus x minus y. So you find dou f by dou x, dou f by dou y, equate them to 0. We get 2x plus y is equal to k, x plus 2y is equal to k. Here why I am using k is it can be any constant, it need not be 100, even constant k. It need not be. In general, you can take k, whatever value you want, 100 or 1000 or 1 lakh, you can substitute there, nothing bothers. So 2x plus y is equal to k, and x plus 2y is equal to k, dou f by dou x and dou f by dou y. Then x is equal to y is equal to k, whether this is the solution of these two. And then find dou square by dou x square, that is minus 2y. Is dou square f by dou xy, and is dou square f by dou y square. Then find the value of ln minus m square. This This is 4x5 minus so on and so forth, and get the values, substitute the values of k by 3, and it will be greater than 0, ln minus m square greater than 0, and L less than 0, so you have a maximum value at k by 3, k by 3. So in place of k, if you put 100, so in fact, and the problem is given as x plus y plus z is equal to 100, you need not use k, even you can straight away do it with 100, as well you can get this answer, 100 by 3, 100 by 3, 100 by 3. So a rectangular box at open top is to have, so 32 cubic feet. Find the dimension of the box requiring least material. Just I'll give the introduction and leave the problem up to you. So volume of the box is, let us say the dimensions of the box is x, y and z. Okay. What is the volume then? If x length, breadth and height of the box are given as x, y and z, the volume of the box is given as x into y into z. That is given as 32. So x, y, z is 32. What is the least material required? Material required is surface area of the box. And how many surface does a box have? In fact, 6. One side, this side, this side, this side, top and bottom. 6 sides we have, but the box is mentioned. It is mentioned that box is open at the top. That means we have only 5 surfaces. xy plus 2yz plus 2z. This is yz. This area of this surface is yz, and same area here yz. This area is zx. Area zx, 2zx. This area is xy, and the top surface is not there, so only one surface xy. So so this is surface area, and we have to minimize this surface area. Least material, that means surface area must be minimum. So minimize yes, but you have to minimize the surface area, but the volume of the box must be same thing, 32 cubic feet. So xyz is equal to 32, so z is equal to 32 by xy. So if you put this surface, this z is equal to 32 by xy in surface area, what we are doing is say 3-dimensional problem, and maximum minimum we have defined only for 2-variable problem. So what we are doing is we are reducing the dimensions, 3 dimensions to 2 dimensions. How? Z is equal to 32 by xy, put it in S. So xy plus 2 into y into z, 32 by xy, plus 2 into x into z, 32 by xy. So this is your surface now, surface area now. For this you have to find the minimum value. So dou s by dou x is y minus 64 by x square is equal to 0. Dou s by dou y is x minus 64 by y square is equal to 0. Solve these two equations, we get x is equal to 4, y is equal to 4. Then find the second derivatives. So this is the extreme value, extreme point. Then we have to find maximum and minimum. For that, ln minus m square test. So L is dou square s by dou s square by x square. That is 64 by x cube, 128 by x cube. M is dou square s by dou x dou y, that is 1. And the other one is n is dou square s by dou y square is 128 by y cube. At x is equal to 4, y is equal to 4. Then we have to find L, M, N. And ln minus m square is greater than 0. So we have a maximum or a minimum. The maximum or minimum, we have to find L. L is 128 by x cube, and x is 4. That means 4 cube is 64. So 2 greater than 0. Then what does it mean? At x is equal to 4, y is equal to 4, ln minus m square is greater than 0 and L greater than 0. That means at x is equal to 4, y is equal to 4, we have a minimum value for s. So s is minimum at x is equal to 4 and y is equal to 4. When x is equal to 4 and y is equal to 4, what is z? Z is 32 by xy. So 32 by 16, that is z is equal to 2. That means, if you go back to the problem now, the dimensions of the box for the least surface area requiring the least material and occupying 32 cubic feet is x is 4, y is 4 and z is 2. Find the points on the surface. So you can just go through this thing that are nearest to the origin. So P of x, y, z be any point on the surface then phi of xy z is equal to z square minus x. This is, I am writing this, z square minus xy minus 1. And if xyz is any point on the surface, OE is the origin, the distance between xyz and OP is square root of x square plus y square plus z. So distance between origin and the point Pxyz. Where is P? On the surface. So find the points on the surface that are nearest to the origin. So this distance we have to minimize. P square is equal to x square plus y square plus z square. And z is equal to z square, because it's three variable function, we reduce the dimensionality. So what is z square? Z square minus x minus 1 is equal to 0. So z square is equal to 1 plus xy substitute here. So this is the function we have to minimize. So this dou square p by dou x square, dou square p by dou x dou y, dou square p by dou y square, and then you find all those things and equate dou p by dou x, dou p by dou y is equal to 0. So we get 2x plus y is equal to 0 and 2y plus x is equal to 0. If you solve them, x is equal to 0 and y is equal to 0. And then z is equal to plus or minus square root of xy plus 1 from this again. So 0, 0, 1 and 0, 0, minus 1 are the critical points. So again, you apply ln minus m square test and L greater than 0 test, and then if you have minimum point at P and Q, required point 0, 0, 1 and 0, 0, minus 1. Okay, so here ends the topic partial differentiation with the maximum and minimum. So now in one variable calculus, we start with limits, continuity, differentiation and integration. Then different integrals, improper integrals. In two variable and three variable calculus, also we start with limits, continuity, differentiability, what we are calling partial differentiation. In the similar lines, what should be the next one? Integration in more than one variable functions. Integration in more than one variable functions. That's what we call multiple integrals. If you simply integrate f of x between the interval between the limits a and b, integral a to b f of x dx, only one independent variable x. But in partial differentiation, what happens? Partial functions of several variables, what happens? We have more than one independent variable. In such case, your usual integration will not work out. Then you have to integrate both with respect to x, with respect to y, with respect to z. That's what we call multiple integrals. And we will deal with this multiple integration in the tomorrow's class. With that, the multivariable calculus, most of the calculus part will be completed, and then we'll be having only vectorial aspects of multivariable functions and what we call vector calculus. Vector calculus is also a multivariable function. We have x-axis, y-axis and z-axis. There are three independent variables. We give vectorial representation for that, right? So that's what is vector calculus. So with this, today I sign off with the after completing partial differentiation. Go through the problems, do the problems. The material is given to you. PPTs will be, I will provide the material to you. They will be uploaded in the website. They may do some problems. Okay, you, I think, practice some more problems. If you have any doubts, you can mail me. Okay, all the best. That's all for today. See you tomorrow again. Bye.